Hi dear students, we were talking about the applications of Gauss's law, and in the last class we discussed the first application, that is electric field due to uniformly charged sphere, and today we discuss the second application, that is the electric field due to an infinite plane charged sheet. Second application, the electric field due to an infinite plane charged sheet. What is this infinite plane charged sheet? The picture shows the infinitely plane charged sheet. That is, this consists of large number of positive charges, for example, and to find out the electric field due to this charged sheet, a Gaussian surface is drawn. That the Gaussian surface is this one. That is, one can easily draw this Gaussian surface, like if this is a charged sheet, positively or negatively charged sheet, then this is a small area in the charged sheet. Then the Gaussian surface can be drawn like this. This Gaussian surface is nothing but called a pillbox. It is Gaussian pillbox. That is, we have drawn Gaussian pillbox. Actually, this is an infinite plane, carries a surface charge density sigma. Then we have to find out the electric field due to this infinitely long plane charged sheet. We have the tool, that is the Gauss's law. E dot surface integral E dot dA is equal to charge enclosed divided by epsilon 0. Then if we consider this Gaussian surface in the figure, we have to evaluate the surface integral E dot dA from this figure. Then how we can find out? This pillbox consists of the side surface. That surface area vector is dA. If this is a surface area, then the surface area vector will be always perpendicular to the plane of the surface. Similarly, here for this region, the electric field, the direction of the area vector will be like this one. Then what about the upper and lower surface? The upper surface, the area vector will be along this direction. The lower surface, the area vector will be along this surface. What about the direction of the electric field? The direction of the electric field, if it is a positively charged, if you refer this figure, that is, from a positive charge, electric field will be emerging away from the charge. That is, if I have a sheet like this, then if it contains positive charge, this is a positively charged sheet, then this will be the direction of the electric field. Because if you have a positive charge like this, electric field will be emerging away from the charge. if I draw the electric field lines of this charged sheet, then this will be this direction, and the bottom of this plain charged sheet will be this way. There will be a large number of electric field lines coming out from the top and bottom surface. This will be the direction of the electric field. If I draw that picture separately, this is our box, field box. The electric field is going in this direction and also through the bottom surface. The area vector of the upper surface is along the same direction as that of the electric field, that is surface vector is dA, and also on the bottom surface the direction of the surface vector is area vector is around the same direction of the electric field. But if you consider the side surfaces, here the area vector is perpendicular to this surface, then the angle between the area vector and the electric field, that is equal to 90 degree for the side surfaces. Situation is same in this side also. If you draw a area vector that should be perpendicular to this plane of the surface, that area vector and the electric field, that makes an angle 90 degree. Then from this one can easily say that the bottom and the top surfaces give rise to an electric field, because the angle between the area vector and the electric field in the top and bottom surface, that is 0, theta is equal to 0 degree, because area vector and electric field both are lying in the same direction. Therefore this will be EDA cos 0, this will be EDA. So this is the small amount of flux that is passing through this small area dA. That is d phi is equal to EDA. If I want to find out the total flux through the bottom surface, that will be phi is equal to integration EDA, that is EA, because electric field is uniform. But for the side surfaces, where the area vector is along this direction and the electric field vector is along per direction, for the angle between them is 90 degree. Therefore small flux through the side surfaces is equal to EDA, that is EDA, this is the quantity EDA cos 90, this is equal to 0. Now let us conclude that the bottom and top surfaces give rise to a flux, that is, here we have the contribution from the bottom surface or the top surface is calculated here, that is, from the top surface or from the bottom surface we will get the flux EA, and from the upper surface, that is, if you look at this figure, from this surface this is also give a flux phi is equal to EA, that is total contribution is EA from the upper surface and this EA from the lower surface. Therefore here I can write EA plus EA, that is a result of this integration, that is equal to the right hand side of the Gauss's law, that is Q enclosed by epsilon 0. Q enclosed by epsilon 0 now I write as it is, Q enclosed divided by epsilon 0. That is, here I want to calculate what is Q enclosed. We know that surface charge density is sigma. Sigma is the total charge enclosed divided by area. Then Q is equal to sigma A. That is, our Q enclosed is nothing but sigma A. Therefore, this is 2EA is equal to, instead of Q enclosed, I substitute sigma A divided by epsilon 0. Here it is very clear that this area and area cancel out. Then the electric field due to this plane charged sheet is given by sigma divided by 2 epsilon 0. This is the magnitude. Then what is the direction? Direction of the electric field, that can be, if this is a plane charged sheet, then this is the area vector whose direction is, I can write dA, or this dA can be written as dA n cap, where n is the unit vector pointing away from the surface, this n. Therefore, the electric field vector of a plane charged sheet is given by sigma divided by 2 epsilon 0 n cap, where n is the unit vector pointing away from the surface. Okay. In the discussion, we had to mention this point also here. That is, the bottom and top surface only contribute to the electric field. There is no contribution from the side surface. The reason is this one. Now let us do a problem in the Griffith textbook. This is the question. That is, two infinite parallel planes carry equal but opposite uniform charge densities plus or minus sigma, as shown in the figure. This is our figure, and this is one charged sheet. It contains positively charges. It contains positive charges because this is positively charged, because plus sigma is given, uniform charge density. And the next is a surface that is negatively charged, that is having the surface charge density minus sigma. Find the field in each of the three regions. That is, first one is the left of both, that is here, left of both. Second one is between them, this in between these two plates, and to the right of both. That is a third region, right of both. Okay, this is the question. To solve this problem, very simply, I will redraw this figure like this one. This is a plus sigma, that is positively charged plate. This is negatively charged plate. If you have a positive charges like this one, and if this is a cross-sectional view of that plane charged sheet, then the electric field lines will be away from these charges. And for a negatively charged sheet, contains large number of negative charges, the electric field lines are going into the charges. And from other side also, the electric field lines always going into the charges. This is the direction of the electric field. This is a region 1, this is a region, I will write this is a region 1, this is a region 2, and this is a region 3. If we compare this figure this is exactly identical to this, and also this. We have to draw the electric field lines in the region 1, region 2 and region 3. The region 1, this plate, that is this positively charged plate, contains large number of positive charges. Therefore, the electric field lines in this region 1 is away. This is because of the these plus sigma charges. Let us write this is E plus. Electric field intensity due to the positively charged sheet. Now, in the second plate, that is negatively charged, it contains minus sigma charge density. This negatively, the electric field lines due to these negative charges, that is always going into the plate. If I am interested to draw the electric field lines in the region 1 only, then I have to draw the electric field this one. That is electric field lines going into the negative, because of the negatively charged sheet, is this direction in region 1. This is nothing but E minus. E minus means electric field due to the negative charges. Similarly, in region 2, the electric field due to the positively charges. What will be the direction of the electric field? Because this is our region 2, if you refer this figure. The region 2, the electric field lines these positively charged is along this direction. Therefore, because electric field lines are emerging away from the positively charged sheet, this is E plus. In the same region, the same place, what is the direction of the electric field lines due to the negative charges? That is, if you refer this again, this picture, the electric field lines is going into this direction, that is into the minus sigma charged sheet. That is, I can write electric field lines is E minus. Then next I have to draw the electric field lines in the region 3. In the region 3, the electric field lines that is coming from this positive charge. If you look at this figure once again, from this positive charge, the electric field lines are going away, like this. Then in the region 3, this is the electric field due to positive charge. That is away. Electric field due to the positive charge is this one, E plus. In the same region 3, the electric field due to negative charge, that is we have already drawn here, that is coming into the negatively charged sheet. Therefore, the electric field lines will be towards this E minus. Now, what is this E plus and E minus? The magnitude is the same. That is, electric field due to a charged sheet which is having charge density sigma is E1 by sigma divided by 2 epsilon 0. Now I take this direction as positive and this direction as negative. Then for this positive electric field, I will write E is equal to sigma divided by 2 epsilon 0 and cap in the positive direction. If it is oriented in the negative direction, like this, I will represent this electric field E is equal to minus sigma divided by 2 epsilon 0 n cap, because it is oriented along this negative direction. If I follow this criteria, then I can write the electric field intensity in the region 1 that is E is equal to, now we have to focus here only in the region 1. The 1 is to the negative direction, that is I can write minus sigma divided by 2 epsilon 0 n cap, that is electric field due to the plus charge. Then electric field due to the minus charges, that is towards the directed towards the positive direction, therefore plus sigma divided by 2 epsilon 0 n cap. See, both have the same, answer will be 0. That is, there is no electric field present in the region 1 because those two electric fields cancel out. They are equal and opposite direction. That is clear in the figure. Now let us calculate in the region 2. The region 2, that is, now you have to focus this region, that is our region 2, where both the electric field lines are oriented on the same direction. Therefore I can write this as electric field E is equal to sigma divided by 2 epsilon 0 n cap plus sigma divided by 2 epsilon 0 n cap. This is nothing but 2 sigma by 2 epsilon 0 is nothing but sigma divided by epsilon 0 n cap. Now in the third region, that is region 3, here you have to focus this area only. In this region 3, we have the net electric field. One is along the positive direction, E plus, can be written as sigma divided by 2 epsilon 0 n cap. Other one is around the negative x direction, therefore minus sigma divided by 2 epsilon 0 n cap. Both are equal and opposite, therefore this is 0. Therefore, for a parallel charged sheet, plain charged sheet, the electric field exists only in this region, that is sigma divided by epsilon 0. There is no electric field outside here, it is equal to 0, and electric field in the third region also 0. Electric field exists only in the region between the plates. The expression for that electric field is given by this equation, sigma divided by epsilon 0. This is the second application. We discussed the third application of the Gauss's law, that is electric field due to uniformly charged spherical shell. Okay. This is a spherical shell. Spherical shell means this is also called a hollow sphere, and since it is uniformly charged, that is sigma is the surface charge density and r is the radius. Now we have a spherical shell. Spherical shell എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ നമ്മുടെ ഫുട്ബോളിൻ്റെ ഗേസ് പോലെ ഇതൊരു ഹോളോ സ്ഫിയർ. അതിൻ്റെ സർഫേസ് എന്ന് പറയുന്നത് ഇവിടെയാണ്. ദിസ് ഈസ് പോസിറ്റീവ്ലി ഓർ നെഗറ്റീവ്ലി ചാർജ്ഡ്, ദാറ്റ് ഈസ് യൂണിഫോംലി ചാർജ്ഡ്. അതിൻ്റെ റേഡിയസ് ആണ് ആർ. ഇതാണ് നമ്മുടെ സ്ഫെറിക്കൽ ഷെൽ. ഇതിൻ്റെ ഹോളോ സ്ഫിയർ എന്നും പറയാം. അപ്പം നമുക്കിവിടെ കണ്ടുപിടിക്കേണ്ടത് ഫസ്റ്റ് വൺ, ദ ഇലക്ട്രിക് ഫീൽഡ് ഔട്ട്സൈഡ്, E outside, then we will find E inside and also on the surface of the spherical shell. To find out the electric field outside, we will construct the Gaussian surface, that is this Gaussian surface has a radius small r. Then we have the Gauss's law, that is surface integral E dot dA is equal to Q enclosed divided by epsilon 0. Here the electric field, if it is positively charged, the electric field is radially outward, and if I consider a small area in the Gaussian surface, that is the area vector, that is also along the same direction of the electric field. Therefore E dot dA, the angle between E and dA is equal to 0. Therefore E dot dA is equal to E dA cos theta, is E dA cos 0, that is equal to E dA cos 0 E dA. This is a small flux through the small area dA. Fine. Since the electric field is uniform, we can take it outside. Therefore E out, if I represent this is a E out, then we have the integration, surface integral of the Gaussian surface dA, that is equal to Q enclosed divided by epsilon 0. What is this surface integral dA? That is surface area of this Gaussian surface. This Gaussian surface is nothing but the spherical shell surface. What is the area of the sphere, spherical shell? The surface area of the solid sphere or the spherical shell both have the same equation, that is 4 pi r square. Then what is the Q enclosed? Total charge enclosed by the Gaussian surface. For that, we know the equation for the surface charge density, sigma. Sigma is the total charge enclosed divided by total area, or Q enclosed is equal to sigma into A. That is, sigma is surface charge density already given. A is the area where the charge contains. If you look at this figure, that is the area is nothing but the area of this spherical shell of radius capital R. Therefore this is nothing but sigma into the area of this spherical surface, that is nothing but 4 pi r square, where you be careful, it is capital R square, because the charge contains in the spherical shell whose radius is capital R. Then we have to substitute this Q enclosed and this Gaussian surface area to this expression. Therefore E out into 4 pi r square is equal to, instead of Q enclosed, we have to substitute this one here. This is sigma 4 pi r square divided by epsilon 0. Here a few times, that is 4 pi will cancel out. Then the electric field outside the uniformly charged spherical shell is given by E out is equal to sigma r square divided by epsilon 0 r square. This is the electric field outside the sphere. Then if you write in the vector notation, this is r cap. The electric field oriented radially outward, that is E out, that is proportional to 1 by r square. Now the second case that we are going to discuss is electric field just on the surface of the spherical shell. This is a radius r, and just on the surface means our Gaussian surface lies exactly at the radius capital R. That is, R is equal to capital R. Then we have the tools, that is Gauss's law. E dot dA is equal to Q enclosed divided by epsilon 0. And we have already developed an equation for the electric field outside, that is this one. Here just we need to substitute capital R instead of the small r. Therefore no need to go for the derivation. We can simply use this equation, that is E at surface is equal to sigma r square by epsilon 0. Instead of small r we can substitute capital R. Therefore it will be r square. Then it is very simple, this r square and square get cancelled. The remaining equation is sigma divided by epsilon 0. Now this is the expression for the electric field on the surface of the spherical shell, sigma divided by epsilon 0. The last case that we are going to discuss is electric field inside the spherical shell. We denote this as E inside. The region that is R less than R. Draw the Gaussian surface. That the Gaussian surface should lie inside the sphere. That is, this is small r and this is the capital R. Remember, all the charges are concentrated, all the charges are deposited on the surface, that is are shown in the figure. That is sigma, all the surface charges are situated at the radius capital R. Therefore, while using the Gauss's equation, that is E dot dA, Q enclosed divided by epsilon 0, instead of integral dA, we can substitute the surface area of the Gaussian surface, that is 4 pi small r square. Instead of Q enclosed, that we need to calculate what is a Q enclosed. Q enclosed means total charge enclosed by the Gaussian surface, total charge enclosed by the Gaussian surface. If you refer the figure, it is very clear that all the charges are situated at the surface, and inside the Gaussian surface no charges exist. Therefore Q enclosed is equal to 0. That is, Q enclosed is equal to 0. Therefore the right hand side of this equation, that automatically goes to 0. Then E into 4 pi r square is equal to 0. That is, a electric field inside a uniformly charged spherical shell is nothing but 0. Now let us summarize by plotting a graph. Before going to the graph, just we have to note down this point. That is, since the Gaussian surface does not enclose any charge, Q enclosed is equal to 0. Yes, we can add a statement here, that is Now I would like to collect all the results, that is E outside we obtain, that is proportional to 1 by r square, and on the surface the electric field is maximum, that is sigma divided by epsilon 0. Let us denote this as a E maximum value, and E inside the electric field is equal to 0. Then if I plot a graph, the graph, this is our spherical shell whose radius is this capital R, and on the x-axis as usual this is R, and y-axis this is electric field E. Then inside means this is the region R less than R region where the electric field is 0. E is equal to 0. Then just at the surface, that is at this point, the electric field is maximum, E max. Then if you go away from the surface, then the electric field intensity, that is proportional to 1 by r square. Therefore here I can plot the graph like this. This is nothing but E is proportional to 1 by r square. This is outside. This is all about the electric field due to a uniformly charged spherical shell. The last application that I am going to discuss today is the electric field due to uniformly charged cylinder. That is the fourth one. It is given that the rho is the charge density, because this is not a hollow cylinder, this is a solid cylinder. Let me note that this is a solid cylinder. Okay. Then whose radius is R, capital R. Then as usual, first we need to calculate the electric field outside. E outside, that is R greater than R. This is our cylinder, and whose radius is this R. To find out the electric field outside, we need to construct a Gaussian surface outside. The radius of the Gaussian surface is small r. Then for this cylinder, if it is uniformly charged, means suppose this is positively charged, the electric field lines will be emerging away, that is along this direction, and this cylinder has two surfaces. Two means curved surfaces like this one, and two flat end surfaces. The area vector of these surfaces can be drawn like this one, and these curved surfaces this one, because here the electric field intensity, the electric field E and the area vector makes an angle theta is equal to 0 degree, but at the end surfaces the electric field is along this the area vector is along this direction, and the electric field is along perpendicular, that is this direction. This E and dA makes an angle. This is dA and this is electric field, angle between them is 90 degree. Obviously, the result, that is E dot dA, goes to 0 because theta is equal to 90 degree. Cos 90 is nothing but 0. Therefore, while applying the Gauss's theorem, that is E dot dA is equal to Q enclosed divided by epsilon 0. Here, the surface, we have the two surfaces. One is the end surface, the flux through the end surface, and plus the flux through the curved surface. E dot is equal to Q enclosed divided by epsilon 0. And as we discussed just now, that is the end surfaces do not contribute any electric field because the angle between E and dA is 90 degree. Therefore, only the curved surfaces, that is as shown in the figure, these curved surfaces contribute total flux. Therefore, I can easily write, if E I take outside, that is EdA, this is nothing but the curved surface is equal to Q enclosed divided by epsilon 0. Then, what is the area of the curved surface? If you refer this figure, that is the solid cylinder has a radius r, and if its length is small l, then the area of the cylinder, that is surface integral dA, that is nothing but 2 pi r, and our Gaussian surface whose radius is small r. Therefore, this should be surface area into its length. If L is the length, then this is 2 pi RL. 2 pi RL. This is nothing but the area of the Gaussian surface. Here the Gaussian surface is nothing but the Gaussian cylinder. Therefore, 2 pi r into L. 2 pi r means that will be the circumference of circle, but since the cylinder has a length, to enclose all this surface area, we need to consider the length also. Therefore, the expression for the surface area of the cylinder is this one, 2 pi r. Fine. Now let us proceed. This is E outside into 2 pi RL, but we need to know what is the charge enclosed by this Gaussian surface. Next, we need to calculate the charge enclosed, Q enclosed. We know it is already given that the total volume charge density rho is equal to Q divided by total charge enclosed divided by volume, that is total charge enclosed means rho into V, where V is the volume throughout the charge is distributed, that is rho into pi. For a cylinder, this is 4 pi capital R square L, because if you refer the figure, all the charges are sitting or distributed throughout this volume. Maybe this may be positively charged or negatively charged, whatever it may be, all these charges are distributed throughout the volume only. Therefore, we have used the capital R. Okay. Then this is quite simple. Just substitute here this Q enclosed. that is rho into pi r square L divided by epsilon 0. This pi and pi get cancelled. Okay, we have already used the length small l, therefore here also I will use the small l. Then the small l will also get cancelled. Then electric field outside the uniformly charged solid cylinder, that is equal to rho r square divided by 2 epsilon 0 r. The electric field is radially outward, therefore this we have used unit vector r. This is the final expression for the electric field due to uniformly charged solid cylinder. That is, here E outside is proportional to 1 by r. This has to be noted. Now, to find out the electric field on the surface, is E on the surface. That is, R is equal to R. Very simple, no need to go for the derivation. Just substitute capital R instead of the small r from the above expression. Therefore, E on the surface is equal to rho r square divided by 2 epsilon 0. Instead of small r, substitute capital R. And this will be vector r cap. Here the r square 1r is cancelled. Therefore, the final expression is rho r divided by 2 epsilon 0 r cap. This is the expression for the electric field intensity on the surface. Now let us go for the electric field intensity inside the uniformly charged solid cylinder. C, E inside. Inside means we have to construct a Gaussian surface r less than r region. That is, if this is our cylinder whose radius is capital R, then the Gaussian surface should be inside. This is R, which means this R is less than R. But this is not a hollow cylinder. This is a solid cylinder. Therefore, the charges are uniformly distributed inside the volume also. But you have to be very careful. That is, to find out the electric field inside the uniformly charged solid cylinder, inside dot dA is equal to Q enclosed by the Gaussian surface divided by epsilon 0. E inside into dA is equal to Q enclosed divided by epsilon 0. Then E inside into the area of the Gaussian surface. Here the surface area of the Gaussian surface means GS. This is nothing but Gaussian surface area. E is equal to 2 pi, since it is cylinder, 2 pi r, where r is the radius of the Gaussian surface, into its length. Length we have chosen small l. Then the charge enclosed by the Gaussian surface, that is Q enclosed. Just now, that is, we know already rho is equal to Q enclosed divided by volume, or Q enclosed is equal to rho into V. Rho into, where V, we have to be very careful. Where V is the volume of the charge enclosed. Here, now we need to consider this Gaussian cylinder and whose radius is small r. Therefore, while substituting the expression for the volume, we have to write pi small r square length L, because the length of Gaussian surface and the actual solid cylinder both have the same length. Now just to substitute the values here, this is 2 pi RL is equal to rho into pi r square L divided by epsilon 0. Few times cancel out, pi get cancelled, r and r, L and L. The final expression, now we can write E inside is equal to rho r divided by 2 epsilon 0. If you write in terms of the vector quantity, that is the electric field is radially outward. Okay, this is the expression for the electric field inside the uniformly charged solid cylinder. E inside is proportional to R. If you remember the expression for the electric field inside a solid sphere, E inside is equal to rho R divided by 3 epsilon 0 R cap. But see here for the solid cylinder, E inside is equal to rho R divided by 2 epsilon 0 R cap. Okay. In this way you can remember these equations. Fine. These are the applications of Gauss's law. Now there are a lot of problems given in the Griffith textbook, and few questions I will give you as assignment, and a few problems we will do in the next class.